the first speaker is Professor Miura. The title of his talk, Rigorous Derivation of the Surface Navier-Stokes Equations by the Thin Film Limit. So please.
So, thank you for introduction. And I'd like to thank the organizers for giving me this opportunity to talk in this nice workshop. So today I talk about our recent result on mathematical rigorous derivation of the surface Navier-Stokes equations by the thin film limit. So let me start with a brief introduction. Fluid flows on surfaces appear in many situations, like soap films, fluid flows in biological membranes, or sometimes geophysical fluid flows on, at very large scales can be seen as fluid flows on surfaces. So Navier-Stokes equations on surfaces, or more generally, many kinds of fluid equations on surfaces are important to model and analyze such fluid flows. So at least we want to formulate Navier-Stokes equations on surfaces, and in the case of fluid flows on in the Euclidean space, the form of it is well known that the Navier-Stokes incompressible Navier-Stokes equations is of this form. So if we consider the generalization or describing the surface Navier-Stokes equations, we may first try to replace each terms of these equations by their surface variants. For example, this part is, of course, the time derivative, so this is the same. We can guess that this is the same. And this convection term can be replaced by the covariant derivative. And also the gradient of the pressure can be replaced by the tangential gradient of the surface pressure, and the external force is the same, of course. And the divergence of the velocity field can be replaced by the surface divergence of the surface velocity. But then one question arises: what is a viscous term? Because in the case of vector fields on surfaces, one can take many kinds of Laplacians, like Hodge Laplacian and Bochner Laplacians and others. And moreover, it is not clear whether or not the Laplacian itself is appropriate for describing the viscous term in the surface Navier-Stokes equations. And one answer to such question is raised by, first proposed by Boussinesq in the context of the two-phase flows, the interface to describe the interface equation of the two-phase flows, and then this generalized by the Scriven to the general moving curved surface. So nowadays, so-called Boussinesq-Scriven surface fluid model is widely adopted in the mathematical and engineering and other fields. And in the Boussinesq-Scriven surface fluid model, the surface Navier-Stokes equations is of this form. In fact, I explain the notations details in detail later. But anyway, we have the time derivative and the covariant derivative and the tangential gradient and the surface divergence. And the viscous term is given by the surface divergence of the surface strain rate tensor on the surface gamma. And today's our aim is to show mathematically rigorously that for a 3D curved thin domain in R3 of a very small thickness of order epsilon, where this is a parameter, a very small positive parameter, if the thin domain degenerates into the 2D surface as epsilon goes to 0, then the well-known 3D Navier-Stokes equations, these equations, becomes this surface Navier-Stokes equations as epsilon goes to 0. So this is the introduction. And now let us explain the actual problem setting. Let gamma be a closed, connected, oriented, and smooth surface in R3. Here, closed means that this gamma is compact and without boundary. And we assume that for simplicity connected, but we do not assume that this is simply connected. So we can consider, for example, sphere and torus and other closed surfaces of genus greater than 1. And we denote by n the unit outward normal vector field of this surface. For this given surface, and for a very small parameter epsilon, we define the curved thin domain around gamma in R3 denoted by omega epsilon by this formula. So in this talk, this curved thin domain is just a tubular neighborhood of the given surface of radius epsilon over 2. But in fact, we can also consider general, slightly general curved thin domain with variable width. For example, in fact, the width epsilon times some function on gamma. But for the simplicity, we focus on this case here. And we also denote by the gamma epsilon 0 and gamma 1 epsilon, the inner and outer boundaries of the thin domain. So this is our this is a picture of our thin domain and given surface. We first give the here given surface gamma, and we have so we give some thickness of this surface to define curved thin domain omega epsilon. And we also denote by the inner boundary gamma epsilon 0 and outer boundary gamma epsilon 1. So, but this is of course 2D picture. So please imagine that 3D version of this picture. And so the typical example is I also show later. Typical example is thin spherical shell, which is a region between the sphere of radius 1 plus epsilon over 1 minus epsilon over 2 and 1 plus epsilon over 2. In this curved thin domain, we consider the following Navier-Stokes equations. The first two equations here is usual Navier-Stokes, incompressible Navier-Stokes equations, but with new the viscosity coefficient independent of epsilon. This is our assumption here. Then we impose this equation. We impose the Navier's so-called Navier's three boundary conditions to these equations. The first boundary condition is impermeable boundary condition, which says that the fluid does not go out or come into the boundary. Come into the curved thin domain through the boundary. And then in the next condition, the fluid can be slipped on the boundary with velocity proportional to the tangential component of the stress vector. And here we have the friction coefficient, which depending on epsilon. In fact, we assume that this friction coefficient is of order epsilon. And this is given by on the inner outer boundaries differently by this formula. And here gamma 0 epsilon and gamma 1 epsilon are given non-negative constants. And we also define the we also impose the initial condition here. So here the gamma epsilon is the union of the inner outer boundary. So the whole boundary is denoted by gamma epsilon. And we have the orthogonal projection onto the tangent plane on the boundary. And we also write D is the strain rate tensor for the bulk velocity. So this is our starting point. And in the study of the others, in the study of the Navier-Stokes equations in 3D thin domains itself, we have, roughly speaking, we have three main problems. It is well known that Navier-Stokes equations, 2D Navier-Stokes equations have the global solution in general, but the 3D case is a millennial problem. But in our case, in this case, 3D thin domains is very close to 2D set. So we first expect to get the global existence of a strong solution for very large data as epsilon is very small. So then if we can get the global existence of a strong solution, then next we are interested in the behavior of this solution as epsilon goes to 0. In particular, we want to show some convergence result of this strong solution as epsilon goes to 0. And if we can get some convergence result as epsilon goes to 0, then we want to know what is the limit. In particular, what equation is characterized by the limit of the solution as epsilon goes to 0. Especially by this characterization, we can derive the limit equations from the sin domain problem. Such problems have been studied by several researchers. The first study was done by Roger and Serre in 1993, and they consider the flat sin domain, flat 3D sin domain of this form with omega rectangle. They studied the Navier-Stokes equations in the, with periodic boundary condition or the periodic Dirichlet mixed boundary conditions to study these problems. And then later, Temama and Ziane generalized the results of Roger and Serre to flat sin domain omega epsilon with general 2D bounded domain omega. And they also consider various boundary conditions like Dirichlet, Neumann, or periodic and something so. And this kind, the Navier-Stokes equations in this kind of flat sin domain was studied by many authors. There are many improvement and generalization of the results of Roger and Serre and Temama and Ziane. But this 3D sin domain is too simple to apply or consider applications to the physical or engineering problems. So slightly different kind of flat sin domain was considered by Iftimi, Roger, Serre, and Wang and others. In their studies, the 3D sin domain is of this form. So this is flat. So this is a sin domain around a square, but which has non-flat top and bottom boundaries given as a graph of functions on the square. And Iftimi, Rogersen, and one others studied the Navier-Stokes equations in this sin domain under the Navier's three-boundary conditions, including the perfect strip and, of course, the partial strip conditions. So there are several kinds of flat sin domains, this kind, but we can also consider curved sin domains around a 2D set, not a flat domain, but general surfaces. And such a study was first done by, in fact, I can find only this paper, but anyway, Temama and Ziane consider the curved sin domain in the study of the Navier-Stokes equations. In their case, the curved sin domain omega epsilon is a region between the unit sphere in N3 and the sphere of radius 1 plus epsilon. And they impose the so-called Hodge boundary conditions to derive the global existence of a strong solution, and also they derive the limit equations on the sphere. But I here remark that their limit equations are different from ours. I explain in detail later. And our case is we consider the curved sin domain, 3D curved sin domain around the general closed surface with non-constant curvatures. So this is a point. Of course, our case includes where the surface gamma is a unit sphere. And we also consider these problems, and in fact, we solve these problems to finally derive the limit equations. So this is the previous works and relation to our case. And so let us state our main result. But before to do that, we need to introduce some notations. So to derive the limit equations on the surface, we want to make a vector field defined on the curved sin domain into some vector field defined on the surface. So we take the average of a vector field U defined on omega epsilon in the thin direction or in the normal direction of gamma by this formula. So we just take the average, integral average in the normal direction or the thin direction of the surface. And we also define the m tau u as a tangential component of the average of U. Here P is tangential, orthogonal projection onto the tangent plane of the surface at each point. And we also define the tangential gradient and surface divergence on gamma as for by these formulas. Here, in fact, the eta is eta must be extended to the some neighborhood, open neighborhood of the surface. But in fact, in this notation, we can use any extension of eta function eta to open neighborhood of gamma. This is well defined notation. And we also use somewhat, we apply each component, the surface tangential gradient of V, and we take the trace of the tangential gradient matrix of this vector field to define the surface divergence. We also, and we note that these definitions are consistent with definition of gradient and divergence on the general abstract manifold. And we and our limit equations, surface Navier-Stokes equations, are the equations for the tangential vector fields. So we introduce function spaces of tangential vector fields on the surface as follows here. So we just take the we just impose the tangential condition here and the divergence condition here. And with these notations, we can state our main result. But for the simplicity, we assume that the external force identically vanish. Under suitable assumptions on the given surface, friction coefficients and the initial velocity belongs to the usual solenoidal L2 solenoidal space and H1 space. Not that this is not the usual. This is not the closure of the smooth solenoidal vector fields in H1 because we just assume that the normal component of the velocity vanishes on the boundary, not the whole velocity. And this is we impose some assumptions here, but it is some assumptions here, but they are slightly complicated to explain. So I omit here. Anyway, so under suitable assumptions on these guys, suppose further that the following conditions hold. The first condition is a condition on the size of the initial velocity. There exists some constant c, epsilon 1, and alpha such that the h1 norm of the initial velocity squared is bounded by constant c. This is, of course, this is independent of epsilon, and constant c times epsilon to the power minus 1 plus alpha. So this right-hand side can be larger and larger as epsilon goes to 0. So very roughly speaking, of course, domain is dependent. Domain depends on epsilon. So this is not the precise statement, but anyways, this norm can be larger and larger as epsilon goes to 0. But as a second condition, if we take the average in the thin direction of the initial velocity, then its tangential component converges some tangential vector field on gamma weakly in L2 sense. So in some sense, if we take the tangential average in the thin direction of the initial velocity, then this is not so large in this sense. We also impose the condition on the friction coefficient. Namely, there exist some constants, non-negative constants, gamma 0 and gamma 1, such that if we divide the friction coefficient on the inner outer boundaries, gamma epsilon 0 and gamma epsilon 1, divided by epsilon and takes the limit as epsilon goes to 0, then we have the then they converge to some constant for in the inner outer boundaries. In fact, this is just constant, so the constant converges to constant. So these are the assumptions for our main results. Under these assumptions, there exists some constant epsilon 2 such that for for all epsilon, very small epsilon between the 0 to epsilon 2, we can get the global strong solution in this class. In fact, usual L2 sense, global strong solution epsilon to the Navier-Stokes equations in the curved thin domain. And so this is the existence result. And so we can take the limit as epsilon goes to 0 for this solution. And then if we take the average in the thin direction and take the normal component of the average, then if we take the limit as epsilon goes to 0, then we have the strong convergence to 0 of this component in this class. So the normal component is not so problematic. In fact, this result easily follows from the property of the average operator and the impermeable boundary condition in the original problem. So the problem is tangential component of the average of this strong solution. And for the tangential component, there exists a tangential vector field of this class. In fact, this is in the flat case, this is the same as Rayleigh-Hopf class for the energy inequality, energy equality or inequality. But anyway, there exists a tangential vector field V in this class such that for each fixed time t, large t, then the tangential component of the average of the strong solution to the bulk equations converges to this V weakly in this class, L2 time and H1 space. So this is a convergence result for the strong solution to the bulk Navier-Stokes equations. And finally, we can characterize this limit as a unique weak solution to these equations. So as I said, this is a surface Navier-Stokes equations with the time derivative the same as in the usual case, and the covariant derivative defined here as a convection term. And as I said, the viscous term is given by the surface divergence of the surface strained tensor given by this formula. In fact, the usual 3D case, we just have here, this part is a Soleil rate, but we multiply the orthogonal projection onto the tangent plane on gamma, both sides, from both sides here. So this is a viscous term, and in fact, we have the friction term or the damping term here, gamma 0 plus gamma 1 V, as a consequence of the friction on the boundary of the thin domain problem. And we also have the tangential gradient of the surface pressure. And in the right-hand side here, 0, because we assume that the external force in the original problem identically vanish. But in fact, if we consider the general external force and some suitable assumptions, we have the external force here. And we also have the surface divergence-free condition as an incompressibility. And of course, we have the initial condition. So these are the Navier-Stokes, our limit equations. And this is the theorem. And the previous theorem is just gives weak convergence. Any non-information about the actual convergence rate. But in fact, we also have the estimate, actual estimate for the difference of solutions here. Under the same assumptions as in the previous theorem, we have the L infinity in time, L2 in space of tangential component of the strong solution, average of the strong solution to the bulk Navier-Stokes equations minus the solution to our limit equations, and the L2 in time and H1 in space difference norm is bounded by here. Here, of course, we have the difference of the initial data in L2, and in fact, we have the epsilon depending term here given by this formula. This is the difference of the friction coefficient on the boundary of original problem, and this is the friction term, friction coefficient in the limit equations. And we also have this additional term as a consequence. Very roughly speaking, the difference or the residual term of how to say convection term. The treatment of the analysis of the convection term. So this is the actual difference estimate, and of course from this we can get the strong convergence of the tangential component of the average of u bulk velocity to the solution to the limit equations if this right hand side goes to 0. So now, before explain the outline of the proof of theorem 1 and 2, in fact 1, let me give several remarks on our limit equations. So when gamma 0 and gamma 1 equals to 0, this corresponds to the no friction case. Our limit equations are of this form here with divergence-free condition. And this equation can be written as, of course, the first two terms are the same, and we move these terms to right-hand side and rewrite this form, where S gamma is given by this formula. In fact, the divergence term vanishes because of the divergence-free condition with surface dilatational and shear viscosity, and this S gamma is so-called the Boussinesq-Scriven surface stress tensor. So this tensor first proposed by Boussinesq to describe the interface viscosity effect in the two-phase flows, and then generalized by the Scriven to the general moving curved surface. And this Boussinesq-Scriven surface stress tensor appear in the, of course, interface equations of two-phase flows and the Navier-Stokes equations on an evolving surface. So, and we refer to the book by Slattery Sakis-O for the general information or the physical background and some history for the Boussinesq-Scriven model and the interface equations, two-phase flows. And we also refer to the results paper by Bose and Proust and others for the mathematical study of two-phase flows with this kind of Boussinesq-Scriven surface fluid model. And we also refer to the papers by Koba, Liu, Giger, and Jankun, Sharsky, Loisken for the derivation and some study of the Navier-Stokes equations on an evolving surface. In their paper, the Navier-Stokes equations on an evolving surface is derived as a single system, which means that without any bulk system, like the two-phase flows, anyway, model. So our, as I said, our limit equations are the surface Navier-Stokes equations with under the Boussinesq-Scriven surface fluid model. And we also note that recently the numerical methods for the full system, this system, was a linearized Stokes system of the surface Navier-Stokes equations have been developed very rapidly by many researchers, like these people. This is of course, this is not complete list of literature, but anyway, this is some partial list. And one motivation to numerical methods for these equations is to calculate something like fluid flow in biological membrane, which is in fact 3D 3D subject, but to reduce the, but of course, the 3D Navier-Stokes equations in the very thin structure is very high, takes very high cost to numerically calculate. So one motivation is to reduce such phenomenon to 2D Navier-Stokes equations to reduce calculation cost to consider 2D case. And our result justifies such motivation in some sense. Because our results derives surface Navier-Stokes equations from the 3D Navier-Stokes equations in thin domain rigorously. And moreover, we want to emphasize that our work first rigorously showed that these surface Navier-Stokes equations can be actually obtained from the well-known 3D incompressible Navier-Stokes equations in the thin domain by the thin field limit. This is the point of our, this is the most important point of our work. And also our limit equations here, the surface Navier-Stokes equations is actually related to the Navier-Stokes equations in the abstract Riemannian manifold. In fact, when the surface velocity is tangential on the surface, we have this kind of identity. Here, the left-hand side is, of course, in fact, the tangential component of the surface divergence of the surface strain rate tensor, which is described in the fixed coordinate of R3. But in the right-hand side, we have the Hodge Laplacian acting on the one forms, and here we have identify vector fields, tangential vector fields, and one forms. And we also have the in the second term we have the tangential gradient of the surface divergence, and we have the Gaussian curvature of the surface here, additional term. And we note that these three terms are independent of the embedding of the surface into R3. So they are intrinsic quantities. So in our limit equations, viscous term here, but this can be written in this form, and we have the divergence-free condition. So our limit equations can be written as this form here. And as I said, in this equation, each term independent. If we, of course, we can take here the general external force. Each term in this equation is intrinsic, independent of the embedding of the surface into R3. And these equations are the Navier-Stokes, in fact, the Navier-Stokes equations on the abstract Riemannian manifold introduced by Abin and Marsden and Taylor. In fact, they proposed that the viscous term is given by the divergence in the manifold of the deformation tensor in the manifold, defined in abstract way in the Riemannian manifold. But in fact, and then calculate showing the some identity like this to get these equations. And this Navier-Stokes equations on manifold are studied by many authors like this. And in fact, the last paper by Prof, Simon, and Wilke deals with Navier-Stokes equations in a hypersurface embedded in Rn+1, something like that. But in fact, their study is in the context of the Navier-Stokes equations in abstract Riemannian manifold, I think. Anyway, so our limit equations also related to the Navier-Stokes equations on the abstract Riemannian manifold. And finally, let us give some comments on the limit equations derived under different boundary conditions. Temam and Tsiane, as I mentioned before, studies Navier-Stokes equations in the thin spherical shell, which is a region between the unit sphere and the sphere of radius 1 plus epsilon, which converges, which degenerates into, the unit sphere as epsilon goes to 0. And they impose Hodge boundary conditions. In their paper, they call the free boundary conditions, but anyway, Hodge boundary conditions, which states that in the first condition, this is the same impermeable boundary condition. The fluid does not go out or come into the boundary through the boundary. And the second condition here, the vorticity curve U is proportional to the unit normal to the boundary, or in other words, the vorticity is perpendicular to the boundary on the surface, on the boundary of the thin domain. Then they, of course, proved the global existence of a strong solution as like our results. And then they derive by showing the convergence of the average in the same direction as epsilon goes to 0, and characterize the limit as a solution to derive this kind of limit equations here. On the other hand, under the perfect boundary conditions, which the first one is the same impermeable boundary condition, and the second one is the slip condition with no friction on gamma, our limit equations on the sphere S2, in which the Gaussian curvature is identically equal to 1, are of the form, this form. So this is the curvature term. And then now we have the difference, exactly the difference, this curvature term, 2V. This difference 2V comes from the boundary conditions, the Hodge boundary conditions, especially the second condition in the paper by Timmerman Tsiane, and the slip boundary conditions in our work, and the curvatures of S2. In fact, if the fluid velocity satisfies the impermeable boundary condition, then the second condition here minus the second condition of Hodge boundary condition is 2 times the shape operator of the boundary of the thin domain times U. And in this case, in the case of thin spherical shell, this shape operator is just almost the same as plus or minus of the orthogonal projection onto the tangent plane of gamma epsilon, the boundary. So that when epsilon is very small, this term is almost the same as plus or minus, depending on the direction of the normal to the boundary. But anyway, plus or minus 2u. So this 2u becomes, this difference 2u becomes 2v in the limit equations. So if we consider the flat thin domains around the 2D flat domain, this difference does not occur. So if we consider the Navier-Stokes equations in a flat thin domain around a flat 2D domain, we have the same limit equations. If we impose a Hodge boundary condition or a perfect boundary condition, we have the same limit equations. In fact, the boundary conditions itself the same. But if we consider the curved thin domain, we have to note that these boundary conditions are different, and this difference results in the difference of the limit equations. So this is the last remark. So now, in the rest of time, let us show the outline and some remarks of the proof of theorem 1. In fact, the existence, convergence, and characterization results. As a preliminary step, of course, we have to show the global existence and some estimates of a strong solution to the bulk Navier-Stokes equations. I don't explain in detail, but anyway, this is of course tough work. Then as the first step, we derive a weak formulation of the tangential component of the average of the strong solution U epsilon. To this end, we start from the weak formulation of the 3D Navier-Stokes equations satisfied by the strong solution U epsilon. Then we take the average in the same direction of the weak formulation here to derive the weak formulation of the average tangential component of the average of the U epsilon on gamma. Then, using this weak formulation, we can derive the energy estimate for the m tau U epsilon of this form. So this is similar to the usual Navier-Stokes equations, but the point is here, this constant Ct, but bound Ct, of course, depends on the time t, but this is independent of epsilon. This is a very important point. Then, if we get this kind of energy estimate, we can use the usual compactness result, weak compactness result. We take the weak convergence of using this one. We can take a subsequence of m tau U epsilon denoted by epsilon n to converge weakly in the appropriate function spaces on the surface, and then we characterize this weak limit B as a weak solution to the our limit equations. This is done by just takes a limit as epsilon goes to 0 in the weak formulation of the average of U epsilon. So we have the characterization, but this is of course weak convergence of the subsequence. So we want to show the convergence of the full sequence as a step 4. Then our limit equations as basically the Navier-Stokes equations in the 2D surface. So because the domain is 2D, we can show the uniqueness of a weak solution to the limit equations, as in the case of the usual 2D Navier-Stokes equations. Then using this uniqueness result to show the full sequence of the average tangential component U epsilon of the towards this solution B as epsilon goes to 0. So this is a outline, and in fact, the step 3 and step 4 is the same as in the case of the usual Navier-Stokes equations. So we omit we omit explanation of these steps. And so let us give some comments to the step 0 to step 2. So as a step 0, we have to show the global existence of a strong solution. The idea is very easy. By the energy estimate, by the energy method, which means that we just take the L2 inner product of the Navier-Stokes equations, and the solution, or the solution times the Laplacian, was a Stokes operator and use some integration by parts and some estimate. By the energy method, we show that the L2 norm of the Stokes half times U epsilon of the norm is bounded. In fact, this is H1 norm of the strong solution is bounded by some constant, depending, of course, depending on epsilon, but independent of time. So in fact, we want to show the uniform bound in time of the H1 norm of the strong solution. So to this end, we have to deal with the trilinear term, which means that L2 inner product of the convection term and the viscous term. And the key tool is a good estimate for this term. Here, good means that which is similar to the 2D case. I omit to detail because it is somewhat wrong estimate. But anyway, so key tool is a good estimate, like 2D estimate for this linear term. To derive this estimate, we use the average operator denoted by M in the same direction. We decompose this vector field, 3D vector field U, into the average first, UA denoted by UA, satisfying this kind of 2D like product estimate. So we take the product of the here just we take just the norm absolute value of average part times another function phi. This is general H1 function on the same domain. We take the product and estimate L2 norm to get this kind of product estimate. Here the point is power 1/2. All powers are 1/2. So this is usually this kind of estimate only available for the 2D domain because of the Gagliard-Niederberg inequality. But in our case, as I said, the thin domain is very close to 2D domain, to the surface, so we can get this kind of estimate, special estimate. But because of the thin structure, we have here something not good term, epsilon to the power -1/2. But anyway, these powers are very important. And also, we also have the as a decomposition, we also have the residual term UR, which satisfies this kind of argument type inequality. So we can estimate the L infinity norm of this residual term by these guys. So this is good estimate. And combining these estimates, we can get a good estimate for this term. So after that, as a step 1, we derive the weak formulation of the average of the strong solution. To this end, very roughly speaking, we take a test function for the limit equation here, and we define the constant extension in the normal direction of gamma, and we take the test function for the weak formulation of the original problem, and then apply this kind of change of variables. So we transform the integral over thin domain to the integral in the over the surface and its normal direction. And here we have, of course, Jacobian, but this is almost equals to 1. So we can further transform this part into this kind of part. So we have here we have the average of the integral of the average here. But of course, in this kind of transformation makes some residual term. And we have to estimate residual term. Very roughly speaking, our weak form of the average of the strong solution is equal to the weak formulation of the limit equation for plus some residual term, and which is estimated by this kind of thing. And to get, of course, we have to show that this CT is independent of epsilon, and to get this, especially this part, we require estimates of the strong solution here. So we have to the L infinity in time, H1 in space norm estimate, and L2 in time and H2 in space estimate here. So to derive the limit equations, the weak solution is not sufficient. In fact, we need a strong solution to the Navier-Stokes equations. So this is a comment on step 1, and in the lastly, as a step 2, we need to derive energy estimate for the tangential component of average. So in the usual Navier-Stokes equations, we can easily get the energy estimate for the approximate solution by taking the approximate solution itself as a test function. But in our case, this is not allowed because the average of the strong solution does not necessarily satisfy the divergence condition. So to overcome this difficulty, we use the Helmholtz decomposition on the surface of this form. And then using the Helmholtz decomposition, we transform the weak formulation of the average into the weak formulation of the solenoidal part. So after that, we can take this solenoidal part as a test function for its weak formulation. Then we get, as in the case of the usual Navier-Stokes equations, we can derive this kind of energy estimate for the solenoidal part, and then we combine the estimate, difference estimate for the original part, original average and its solenoidal part to get the same type of energy estimate. But anyway, actual calculations somewhat involved. So the time is almost up, and I stop here. Thank you for your attention.
Thank you, Professor Miura, for your nice talk. So now, do you have any question or comment? Okay, please, Professor Terasawa.
So your method is related to the work of Tsian and Tema?
Yes. In fact, Temama and Tsiane also takes the average to derive the, of course, to derive the global existence and to derive the limit equations.
Mm-hmm. Okay, so what is the main difference of their work? Or?
The difference is, in fact, the difference is limit equations here, as I wrote here.
Okay.
Very roughly speaking, the existence results and the convergence results are very roughly the same as in the case of Temama and Tsiane.
Okay.
But the limit equations are different. Yes.
Okay, thank you very much.
Are there other questions or comment? I have one question.
Yes.
Can you see me your main theorem, maybe theorem 1?
Yes.
Next pages.
Okay. Yeah.
Yes. You said in your case, it's very close to 2D case. You can get a global solution. So
yes.
I think it's in that case you need a very small epsilon, very
yes, yes.
thin domain.
Yeah.
This is described by epsilon 2.
Yes. To be precise, we just we first find epsilon, very small epsilon 2. To get the global existence of a strong solution to the 3D Navier-Stokes equations for all epsilon between the 0 to epsilon 2.
Oh, okay.
So we can take the limit as epsilon goes to 0.
Oh, okay. So what kind of quantity does this epsilon 2 depend on?
It is. It is difficult to explain, but I think I think it depends on, so of course, gamma and some basically gamma, I think. But in fact, we have to show some inequalities by the how to say contradiction argument. Some inequalities in the sin domain, uniform estimates for the sin domain by contradiction arguments to get something like this epsilon 2. So the how to say, so concrete dependence is not available.
Okay.
In fact,
okay.
Yeah.
Okay, thank you. Okay, so now is the time. Thank you again for the Professor Miura. Thank you.
Thank you.